We will use the chi-squared test of independence when we have two categorical variables. So if you kind of notice the theme of this, the first one was categorical, the second one was quantitative, the next one was quantitative categorical, and then this one is two categorical variables. We will use this test when we have two categorical variables and want to see if the variables are independent of each other or not. See, if you don't think about it, it's easier to type. If you start thinking, you're like, I don't know how words are spelled. You know what to do. Type in long enough. So what we have right here is we have two categorical variables. Maybe we want to see if freshmen like cats more than dogs, or versus seniors. I can't speak today. If freshmen or seniors like cats or dogs more. So we'd have to ask someone, are you a cat person or are you a dog person? And so that's one variable, cats, dogs. And then we have another variable, are you a freshman or are you a senior? Does everyone see that right there? This one's going to be a little bit complicated because this is our last lecture and the math is going to be a little bit bigger on this one to get the chi-squareds. But luckily the questions are a little bit easier. So we have, and I'll give a different example here. We could see maybe, we always do like UT and Florida students. So we compare UT and Florida students and we ask them, do you think you'll go to a bowl game? So which school thinks that their school will go to a bowl game more? Does it depend on the school you go to or is it independent of the school you go to? And by dependent, that's the same thing as not. By dependent is not independent. So it's either independent or not independent, and not independent, let's put a side note right here, is the same as dependent. So is that clear right there that those things, independent, and not independent means dependent. But I like to say independent and not independent. So now we need some notation. Let's do some notation right here. Notation. So we have here observed values. These will be noted as O, and so let's just put that right there. So these will be the actual amounts people report. We have here expected, which is E. No, don't do that. The expected value for people to report. We have here, let's see, observed minus expected, squared over expected. We have here the chi-squared test statistic. This is going to be a fun test. And let's insert into here. We need an insert symbol, chi-squared. So let's go to equation. Do we see a chi? I might draw the chi. So chi is our little x. Where's it at? I'm totally missing it, and it probably is right in front of me. Oh no, we might have to draw it. Let's draw it out. So chi-squared is going to be our test statistic. How does the chi-squared look? A lot of people say chi-squared, but it's actually chi. So we're going to draw it right here. And so let's write it first. It's spelled C-H-I, but remember it's not chi, it's chi-square. So chi-square test statistic. And we'll put a little parentheses right here. And I'll draw it. So it's like an X with a little tail at the end of it, and it's got the square on it. So I'll draw it really big so everyone can see it's like this, and then you little tail on it, and you do that right there. That's a chi-square. That is the chi-squared test statistic. So you can see what's going on right there. A little hard to draw in the littler box, but let's get one more shot here. Let's do a little tail thing on it, and then do that, and do that right there. It's a great looking chi-square right there. So that is the chi-squared test statistic, and what that is right there will be, basically, let's try to make sense of it as we talk about it. It's basically our T or Z now. So this will be our T or our Z that we're basically using, and it's going to give us the standardized difference between the two. So basically, I don't want to basically, the standardized difference between observed and expecteds. Expected, sure. We're going to square it. We'll look at that in a second. Used to find p-value like the T and the Z. So it's very similar mechanically what we're going to do with it, and luckily for us the test only goes one way. So it only goes to the right. There's going to be a lot of calculations here in a second. Let's write an example problem. So we have here that we will need to, and let me write a few more things. I can't write more things. We'll watch it as we do it. So we need to write an example question. Let's write here, example problem. And what do we have? We have UT wants to see if there is UT and Florida students report if they think we will go to a bowl game. Let's say 70 UT students think we will go to a bowl game, and 30 say we won't. Why did they say that? 50 Florida students, let's do a meanwhile. Meanwhile, we'll do proper grammar. Meanwhile, 50 Florida students say we'll go. At UT, 70 students think we'll go to a bowl game. Meanwhile, 50 Florida students believe they will go to a bowl game, and 50 believe they won't. Okay, go to a bowl game. There we go. And let's see right here. These students were taking randomly. So I want you to look at this question right here. This is the big part of it. When you go up to someone, you'd have to ask them, are you a UT student? Are you a Florida student? And I hope, I'm gonna see if the audio is still going. I should have been watching that all the time. That'd be so sad if we haven't had audio for this. Yes, we got audio. Whew, I'm gonna watch the audio because we have had the audio go out. And since we only have very few people watching, I'd hate for our audio to go out suddenly. That would be hilarious. But with this right here, these students were, there is audio. It's so good to hear that. I'd feel so bad if I'd been doing this for like the last hour and it was all muted. That'd be so horrible. And good to see you here, Bethlehem. Good to see you in the chat. So these students were selected randomly. We are good to go on this. Guess what? Now we're going to go up there and we're going to take our 4 steps to doing this. Well, we could say, let's write this right here. Yes. Is there, are these 2 variables independent? 2 variables, let's say, is the school, oh, it's doing lag? Someone attends independent, how do I not know how to spell when I slow down? Independent of them thinking they will go, their team will go to a bowl game. Okay, so that's kind of the clue right there. Is the school someone attending? Is the school someone attends? Does the school someone attends? Is the school someone attends independent of them thinking they'll go to a bowl game? Let's go with that. Grammar, we're not here for that. Let's go grab our 3 tests. Here's our 3 tests. We got, or not our 3 tests, our 4 steps. Our 4 steps will be used once again. So let's do it. We're going to go down to a new page, or we're going to go back to the problem, and then we're going to go to a new page on the problem for our 4 tests. Okay, we need to write out the null and the alternative. Guess what? When you do these nulls and alternatives, you will not use statistical notation. For once, I hear people cheering already. You will not use statistical notation. You will simply write, well, don't just write this. You'll hear more in a second. You'll write x is independent of y. And you will write, for the alternative, x is not independent of y. Now don't just write this right here because you have to tell me what x is. School is independent of bowl game prediction. And then we could just take this and we would write school is not independent of bowl game prediction. So school is not, we'll fix this here, independent of bowl game prediction. So that is our null and that is our alternative right here. School is independent of bowl game prediction, and please note that what we have going on right here is we're going to make sure you guys know that this is the x variable right here. School is your x, and bowl game prediction is your y. So you just say x is independent of y, someone's school is independent of what they think about bowl games, their bowl game prediction, and then the alternative would be school is not independent. Very easy one to write out. 2 categorical variables. The school someone goes to is categorical, and the bowl game prediction they have is also categorical. Do you think we will go to a bowl game? We will have degrees of freedom in this once again, so Sorry, I missed a little bit on the notation. We've gotten most of the notation, but let's continue on here. Those are calculation things. Degrees of freedom stands for DF, for degrees of freedom. So let's perform the t, z, or chi-squared. This one's complicated. So what do we need for this? Whew, it's gonna be a lot of fun. We need to draw this out. Okay. What we would get on the test is something similar to this. We would have UT, and we'd have Florida. We would have yes, and we would have no. And I think I said 70. How many UT students did I say said we'd go to a bowl game? 70 and 30. Cool. So we have 70, 30. Then we have 50, and we have 50. This one is more complicated. It's going to be a lot of fun. There's the 100 UT students, 100. Here's the 200 total. Here's 80, and here is 120. So there are all the numbers we get on the test usually. And if you notice, you might be, sometimes we leave out one of these. Here is a count missing. These are the observed counts. They can be called observed. If we left that out on the test, then you would just say, okay, wait a minute. The total for UT students is 100. So then if we left out that value, this has to be 30. Just kind of showing what some test questions could look like. We can sometimes leave out values. These are all the observed values. And now we need to find all of the expected values. And I'm going to show you a trick. The formula for the expected values, which is what I talked about earlier, every expected is equal to, so all the expected values equals row total, that's row total, times column total over grand total. Just to be clear, what are row totals? These are row totals. What are column totals? These are column totals. What is the grand total? That is the grand total. So that is the grand total. The row totals are right here. Those are the row totals. And this is the column totals. Those are the column totals. Now we're not going to do them all at one time. You'll see how it's done. Whenever you're finding out an expected value, I want you to do this. This is my favorite way to solve it on the test. Take your pen and be like, okay, they want me to solve for the expected one right here. If we're solving for Florida, yes, you would take the row total times the column total over the grand total. And do you know what you just did? You wrote the equation. Row total times column total over grand total will give us the expected value for that cell. So in that cell, which I'll draw here in a moment, is going to be 100 times 120 over 200. That will be the expected value for that cell. So let's reverse time here and do that. And I'll probably write a few of these out as we do this. Let's erase all this and let's put an expected matrix over here. So we're going to draw an expected matrix. Sure, now let's make it a little smaller. Perfect, that's what we want. And now we need to do this all right here. We have UT, we have Florida, and we have yes, and we have no. These are all expected values. These are all the expected values. We're going to compute them all. So we're going to compute that bottom left one right away. The bottom left one can be done by 120 over 100, 120 times 100 over 200. That is row total times column total over grand total. So let's solve it, and then I'll show you a trick. 120 times 100 over 200. Row total times column total over grand total, it is 60. So the answer to that equation that I just wrote out right there is 60. So let's put 60 in the cell right here. That is how many Florida students we would expect to say yes. But do you know what's interesting? I can tell you that Florida no is going to be 40. It should be. Hopefully it is, or else I've done something incorrect. Let's check. You should be saying to me, Brian, the formula for that one is going to be, I'm trying to erase that little red dot I got right there. Oh no, we don't want to erase that. 2 seconds, give me a shot. That red dot's here to stay. Let's go here, row total. Doesn't matter which order we do it in, times column total over grand total. If you notice, there's the equation, 80 times 100. That points to the cell. Look at the way it points. It points right there to that cell. That is the cell I am solving, and that equation should equal that. We're going to double check the mathematics just in case I maybe made an error. Hopefully I didn't. But let's see. 80 times 100 over 240. How did I know that? Well, think about this. What did these numbers have to equal up to? 60 and 40 have to equal 100. So since I knew 60 and 40 or 50 and 50 equal 100, I know 60 and 40 have to equal 100. Now you can solve out the remainder of these if you want by doing them all by hand, such as 120 times 100, because you can do it either way, over 200. If you notice, that's actually the same value. We're actually going to get the same value as we did previously, and we'd get 60. And then the same thing would occur there, and we'd get 40. If you notice, these add up to 120 and these add up to 80, which are the respective values for the totals below. So your expecteds have to equal up to the row totals and column totals that they were taken from. And of course, the grand total has to be found in what you have too. We're almost done. Ooh, the math for this one is quite fun. But now we need to find the chi-squared test statistic. So let's go down here and find the chi-squared test statistic. Those are the expecteds. So with our expecteds found, we have to do one last formula here, and this is what we'll be covering next class. We need to do the formula, which is observed minus expected squared, quantity squared, over expected. This equals to a cell chi-squared. This is equal to a cell chi-squared. Observed minus expected squared over expected is equal to a cell chi-squared, which means, yay me, and we don't write test questions this long usually, I have to solve out all of these. So I'm going to write out this for you to see right here. We're just going to do a little practice of it. In this cell right here, I need to make my chi-squareds. So if we go here and we write a chi-squared right here, these are the cell chi-squareds. So these are all my cell chi-squareds. I want you to look at the observed for this cell and the expected. Remember, the formula is observed minus expected squared over expected. And I did put the expected there. Hopefully I don't make any math errors. But this is observed minus expected squared over expected. Luckily, since we're squaring it, it doesn't matter which way we subtract it. But in that cell, let's erase all the mathematics we drew out. What are we going to get for the first cell chi-squared? If you notice, it's 70 minus 60. We're going to square that, so we get 100. And then we're going to divide that by 60. And the first cell chi-squared is 16.666. Did I do that right? No, I think I made an error. I typed 6. Because I was thinking that's not what it should be. There you go. So I forgot a 0 on the 6, and that's how errors can happen. Hopefully we haven't made any today. So the cell chi-squared here is 1.6 repeating. And then the next one, we're going to do observed minus, so we have observed of 50. I'm doing the bottom left one now, Florida, yes. Minus this, we're going to square that, that's 100. And then we're going to divide that by the expected. Do not divide by the observed. And once again, we get 1.666 right here. And now we have to do 40 minus 30. This will give us a little bit of a different number. But, 30 minus 40 to be technical. 30 minus 40. And that gives us 100 again when we square it. And then we divide that by 40. You might say, why are you dividing it by 40? Well, it's because, and let me explain why with the next one. We are doing observed minus expected, so it's 30 minus 40 squared, which gives us 100, over the expected. The expected is the equation, observed minus expected over expected. That's what we're solving out right there, observed minus expected over expected. So just notice how I have my observed matrix, my expected matrix, and now I'm getting my cell chi-squared matrix. And the last one right here, the final cell chi-squared will also be 2.5. So that's what we got going on. We're almost done. We're on the downhill on this one. Woo, we got it. If I am correct, I believe the test chi-squared is going to be 8.33. All we do to get the test chi-squared is we add up all the cell chi-squareds. By adding up all the cell chi-squareds, we should get, I believe, 8.333, and we do. All you're doing to get your test chi-squared is, so let's write chi-squared equals sum of cell chi-squareds. So all I did was add up all those values to get the test chi-squared. One more step and we're done. To find the p-value, we have to plot this. The degrees of freedom for this are simply, and it's such a fun thing to do, the degrees of freedom for this one are n minus 1, so let's write here df, and that's not OF, that's df, equals rows minus 1 times columns minus 1. So let's write it so you can see what it's not that hard to write out calls and rows. So rows minus 1 times columns minus 1. That's columns minus 1. What are you doing? All you're doing is taking and deleting one row and one column. How many degrees of freedom does that make when you do 2 times 2, you subtract from that and do 1 times 1? There is 1 degree of freedom for this. So the degrees of freedom for this test are 1, and here's how I ask my students to remember it. When you think about this test right here, if it's a 2 by 2 matrix, hold up your hand with 2 by 2, and then 2 times 2, drop it to 1 times 1. What if you had a 2 by 4 matrix? There's different ones we can do. If it's a 2 by 4 matrix, drop it down to 3 times 1. A 2 by 4 matrix would have 3 degrees of freedom. And you can double check this out right here. You can make sure by drawing a 2 by 4, 2 rows, 4 columns. And you go 1, 2, 3 right there. And then what do you get? If you delete off 1 row and you delete off 1 column, lo and behold, there are 3 degrees of freedom. So that's a 2 by 4 showing that it has 3 degrees of freedom. Just kind of drawing that L, delete 1 row, delete 1 column. Do not think this is a 3 by 3. There are UT students, there are Florida students. There's yes, there's no. It's two two-level categorical variables, and that's what we have going on right here. So we now have our test chi-squared, which was equal to the test chi-squared. So that is the test chi-squared is 8.333, repeating, and the degrees of freedom are equal to 1, and we're almost done. We have now the chi-squared test statistic. Find that p-value. Woo, on the downhill. So now we need to go back to our site. Back. And here we are. Let's put in the degrees of freedom is 1, and let's do it. The chi-squared is a bit of an interesting distribution. It's a right-skewed distribution that actually becomes more normal as the degrees of freedom get higher. But we notice here that ours is very right-skewed due to low degrees of freedom. And look at that p-value. We got basically no area under the curve telling us our results or results more extreme were unlikely due to random chance. You know what we're going to do. We're going to reject that null. So the p-value here is 0.004. It is harder to draw out the chi-squared. I will say this, this question is one of them. If you've done enough chi-squareds, you know a chi-squared of 1 is this heavily skewed distribution. Chi-squared of 1 is extremely right skew. It looks like that, and usually about after 3 you've got a decent hump. That's like a chi-squared of 3, and then after you get to maybe around 30 degrees of freedom, it starts to look pretty normal with the center being the degrees of freedom. So you can see right here with 3, you start to see the bump right there, and then if you get to 30, it starts to look somewhat normal, and then if you get to a high enough, which that is not calculating properly, because the degrees of freedom should be the center of the curve. These are things you don't need to know right now, but you should just know to go to the applet and put in your degrees of freedom. This will draw the curve out for you. We're then going to plot our chi-squared right here, and we're going to find our p-value. And since the p-value is low, what are we going to do? P-value is low, reject that null. You know what's happening. Let's take a look back here. So the truth is we do have this curve right here. We landed all the way here at 8.333. This is a very small p-value. Was it 0.004? I think it was. We're going to double check that p-value. 0.004, if you can't see, there's the p-value right there. My drawing on this one is not as pretty as the other ones. So the p-value right here, that is the p-value right there. When the p-value is low, we reject that null. Good job for UT. We're going to end on a high note for Rocky Top today, because we're going to say we reject the null hypothesis that school is independent of views on bowl game. We have evidence to suggest, thank you, to suggest that someone's view on a bowl game is not independent of the school they go to. Sometimes on follow-up test questions, we've asked you to maybe tell us what direction does it go. And you know what? We're going to end, because I really want to see how right we were. We're going to throw this into jump real quick right here and make sure we did it correctly, and we're actually going to view the visualization of it. So let's hop in here to jump, open up a new data sheet, and do it. So we need right here is school. And we need right here is bowl game. And this will be help for the homework assignment if you're doing those. You can enter this into jump. So this is a little homework help. and you need here frequency. It can be called whatever, but nicer to call nicer things. We have school UT, Florida, Florida. Then we have bowl game, yes, bowl game, no, bowl game, yes, bowl game, no. And I think I said 70 UT students and 50-50 for Florida. So as long as I put in the right numbers right here, and then 50-50, and what do we notice? Let's do the fit y by x. This is recorded, so you can slow it down later if you like. Let's put this into the frequency. That's just the count. We want to see if somebody's school, remember when we said school is the x, explains the bowl game, and let's go here to calculate. And what do we see? Pearson. Pearson's where your p-value is at. Remember that p-value of 0.004? We did that work by hand, and we got that Pearson chi-squared of 8.333. So